instructions between two waypoint instructions on its own. This is especially problematic if there are conditional instructions between two waypoint instructions, because this means we have no trace data that could indicate the execution status of these conditional instructions. The benefit of this approach is that the trace format is more compact, and the trace data rate can be reduced effectively. Let's have a closer look at the waypoint instructions. Basically, we have three types. Waypoint instructions are direct branches, indirect branches, and exceptions. What they have in common, that they result in a change of the control flow of the program. And nonetheless, because the trace information reflects all the changes of the control flow that have occurred during the program execution, it is nonetheless possible to for the trace tool to derive the whole program flow that was executed from the available trace information. Another important point for the tracing of operating systems is the handling of virtual memory management. Basically, this problem is based on the translation of virtual to physical addresses that has to be resolved by the trace tool if the trace data is processed. And there are two approaches for this translation. The first one is based on the data tracing information. The context or the processed thread information can be derived from write accesses to certain memory locations that can be verified by monitoring the data trace information. But the disadvantage of this approach is that the ARM core needs to support data tracing to have access to the data trace information, obviously. So we require an alternative approach for cores without data trace support, and this relies on the so-called context ID register. And this register can be used by the operating system to store the current context information of the operating system, and the trace can be configured in a way that it emits so-called context ID trace messages. These messages indicate these context switches, and so we have the information that we require for the trace processing. A lot of operating systems support this context ID trace register, but not all. And if the support is not given, we have to apply a patch to enable this support. If you compare the two methods, the method 1 should be the preferred one because it does not require any support of the operating system. Here's an overview of the capabilities of the different ARM cores. And you see most of the architectures would support both methods. The Cortex M3 and M4 have no MMU and therefore no memory management. They only have some kind of memory protection scheme. And on the bottom left side we see that some of the Cortex A cores do not have full data tracing capabilities, and that's why method 1 cannot be applied. In the next chapter, I'm going to discuss the basic modes of operation of TRACE32 that are used for trace evaluation. We have 3 modes of operation, which alter the way the data is processed and stored. We have classic tracing, we have streaming, and have real-time streaming. Classic tracing uses the trace buffer as primary storage location, and the trace buffer is located within the trace tool. The second one is streaming, and streaming uses the hard disk of the host during recording, and the trace data is is basically streamed to the hard disk of the host, and real-time streaming establish a simultaneous recording and processing of the trace data. I'm going to discuss this in detail. We have here the overview for clustering tracing. The basic procedure consists of two steps. We have the recording step and we have the processing step. During the recording step, the trace data is transferred to the trace buffer within the trace tool. And if the core execution is stopped or the trace buffer is completely filled, the execution has to be stopped and the recording step aborted to start the processing step. The disadvantage of this approach is that the recording duration is limited by the size of this trace buffer. During the processing step, the trace data is transferred from the trace buffer within the trace tool to the host where it is processed. We offer 4 kinds of trace tools. We have the PowerTrace Ethernet, which is a standalone trace tool which doesn't require an additional debugging tool. Then we have the PowerTrace2, which has a faster interface, but requires one of our debug tools. Then we have the Combi Probe, which extends the function of one of our debug tools to tracing. And then we have, at last, the MicroTrace. And the MicroTrace is designed for the tracing of the Cortex M family. And obviously, all of our tools support this classic tracing approach. Streaming tries to get rid of the flaws of this classic tracing mode. We also have 2 dedicated steps. We have the recording and the processing step. But this time, during the recording step, the trace data is also streamed to the hard disk of the host, while it is also recorded to the trace buffer. And what this effectively does, it increases the size of this trace buffer by the size of the hard disk of the host. And obviously, the hard disk is much larger than this trace buffer, and so the recording duration is extended. Basically, it can be recorded infinitely. I would say there should be no restriction anymore on the recording duration if you use streaming. If the recording has finished, you need to process the data again. Here's the support for streaming, and all of our trace tools support streaming, excluding the PowerTrace Ethernet, because the PowerTrace Ethernet has the problem that the communication interface to the host is too slow, and it cannot keep up with the data rate of the trace, so the trace buffer gets too full before the data can be transferred to the host. The most sophisticated mode of operation is the so-called real-time streaming. For real-time streaming, the recording and the processing step are merged. This means it works at first quite similar to streaming. From the trace buffer, it is streamed to the hard disk, and then it is also processed at the same time. This means you effectively save, if you use real-time streaming, you save the time that would be required for processing otherwise. And if you compare this, you can save with real-time streaming in comparison to streaming a lot of time. The trace buffer is responsible to even out peaks in the data rate of the trace data and to force a constant data transfer rate to the host. One other major important factor for this approach is the processing performance of the host, because also this processing performance has to keep up with the data rate of the trace port. for the support of real-time streaming, the same applies as for streaming. To wrap up the section, I'm going to give a short overview over the basic modes of operation. The classic tracing mode is intrusive because you have to stop the execution if the trace buffer of the tool is completely filled, whereas streaming and real-time streaming are non-intrusive and also allow to continue recording for a very long time. Real-time streaming allows, in addition, on-the-fly processing of the data, but is restricted to ARM cores, which have either the ETMv3 trace protocol or the PTM. Streaming and real-time streaming are not supported by Powered Ethernet modules. Let's come to the code coverage approach. But before we come to TRACE32, I'm going to give a short explanation of the term code coverage. Code coverage is a direct measure to which extent the code of an application has been executed. What you, the primary application for code coverage is doing software testing. You can do your software tests, and after you're finished, you can analyze the code coverage, and then you can say which part of your software have been executed or have been exercised by your tests. A common misconception is that there's always a correlation between high code coverage and quality. This is not true in general, because you can have a very simple test that achieves a high degree of code coverage, but does not really test anything. That's always possible. However, safety standards make heavily use of code coverage criteria, and they do this because they have a requirement-driven approach, meaning all the tests have to be derived directly from requirements. And if you are not able to satisfy all code coverage criteria, basically what you have to do, you have to go back to your requirements and to have derive additional test cases. If you have no requirement, you have to first generate a requirement and then derive your test. And if you have finally satisfied all your code coverage criteria, you have basically shown that your application works as intended, and it works in compliance with your requirements, which proves a certain level of quality of your software.